Hello and welcome to everybody to my short video to show you some neat, sometimes overlooked analysis capabilities of the Anritsu MP1900A signal quality analyzer. This is targeted for hardware designers in the high-speed computation, automotive and communications industry. My name is Martin Storch, an EMEA Anritsu Field AE for birds and high-speed optics located in Berlin, Germany. I'm in the test and measurement industry for more than 20 years now. As many hardware engineers choose oscilloscopes as one of their basic tools for design, characterization, and troubleshooting, this video will highlight some very effective analysis features of the Anritsu MP1900 bird system, beyond its role as a mandatory integral part of compliance tests for many technologies. Bird systems like the Anritsu MP1900A are being used for compliance tests for high-speed computer bus technologies and Ethernet-based technologies. I have put up some examples at the right side. PCI 6 stands for PCI Express, IEEE for Ethernet, and we all know USB. This is to ensure that all components of all vendors interoperate with each other. For instance, a PCI Express graphics card of vendor A with a PC motherboard of vendor B. I'll start with a brief overview of a bird system and the concepts of high-speed receiver testing. Then I'll show some neat, very useful troubleshooting features on my MP1900A bird shown in this picture. This picture shows a typical measurement setup for a bird system. A bird typically consists of a pulse pattern generator, or PPG, plus additional signal stressing modules for jitter and noise, and an error detector. As it shows on the picture, the PPG feeds a stress signal to a DOT, device under test, to simulate real-world or worst-case conditions for the DOT's receiver. In order to measure bit errors at the RX side, the received data has to be resent by the DOT's transmitter to the error detector. In order to do this, the DOT has to be in the so-called loopback mode. What's the purpose of predistortion? In order to compensate for high-frequency signal losses on communication links, many technologies are using predistortion techniques called preemphasis, deemphasis, pre-shoot at the transmitter. High-frequency parts of the signal around bit transitions are amplified because they are mostly affected by the link's bandwidth limitation and therefore attenuated. PCI Express and USB define certain setups of deemphasis and pre-shoots, which are called presets. I'll show and discuss them later during the demo. On the picture there's a device called RTO, a real-time oscilloscope, which is required for compliance test, but also highly recommended to have it next to the error detector to investigate possible pattern sync issues on the error detector. Before I start with specifics about high-speed bus measurements, let me give you an overview over the MP1900 signal quality analyzer. It is a modular, highly flexible and future-proven bird system for a wide range of applications. High-end research on 400G or 800G and beyond due to its up to 116 gigabits per second PAM4 support and multi-channel capability. As PAM4 will be used in PCI Express Generation 6, the system hardware is ready for Gen 6 today. 10-tap emphasis is required for PCI Express USB preset generation. PPG and error detector are protocol aware to bring PCI Express and USB DOTs into loopback mode during a successful link training. I'll come back to this topic soon. Powerful forward error correction handling and PAM4 are required for faster than 100G Ethernet. No external boxes are required for PAM4. Generation of those signals never has been easier. In the end, one system, sometimes even the same modules, can be used for high-speed bus and Ethernet applications. As Anritsu doesn't have real-time oscilloscopes in their portfolio, it is important to know that we provide compliance solutions with all big scope vendors. This picture displays the necessary steps through a receiver compliance test for PCI Express and USB. While the calibration is beyond the scope of this video due to its complexity, I want to explain the link training as a precondition for communication between link partners, for example between graphics card and motherboard or MP1900A and the DOT. PCI Express and USB Gen 3 and beyond both use link training to establish the optimal transmitter and receiver setups depending on the link quality like loss and jitter and the link partner's properties. Most important, the optimum presets and data rate to be used for data transmission are negotiated during the link training. In case link partners are of different generations, the lower data rate is being used. On my following live video, I will demo the link training and based on this, show and explain some very useful analysis features like matrix scan and jitter tolerance. Let's watch it live now.
Here you see the GUI of our BIRD system. On the right side you can see all the available modules. Two of them are highlighted in green. That's the ones which are displayed. On the left side the pulse pattern generator module, on the right side the error detector module. Remember, when I mentioned the link training required to establish a link between the sites. One of the negotiated parameters is the preset, the amount of predistortion best suiting the link characteristics. PCI Gen 4 has altogether 11 presets. Currently preset 4 is selected, showing no predistortions at all. Now I switch over to preset 7. And as you can see, preset 7 shows pre-shoot, the spike before the edge, and de-emphasis, causing the undershoot after the edge. Now let's have a look on the error detector. This module will count errors on the specified pattern, continuously and as long as required. Please have a look at the 3 CSE indicators on the top of the error detector screen. C stands for clock, S stands for pattern synchronization, E stands for bit errors. Currently C is red because the PPG is switched off, so there's no signal on the error detector input. Let me turn it on. So I'm turning on the PPG. Now you can see the clock indicator turned black, but the synchronization lamp shows red. This is why I've selected the wrong pattern on the error detector side. Let me change this to PRBS 15. And as you can see, currently the link shows error-free. And now I can start the measurement because we are synchronized on the pattern. So let's start the measurement and look at the results. Press start and look at the results. So as you can see, we are currently error-free. So it's time to create some errors now. The PPG allows you to create errors manually or at the specified rate. Please have a look. Go to the Error Addition tab, select bit array, for instance, to 10 to minus 3, put it on, start the measurement, and we see the error rate is at 10 to minus 3. Now that we have a basic understanding of the system, let's move on to some very neat analysis features helping the engineer troubleshoot and optimize their devices. These features are all realized by our high-speed bus application running on top of the BIRD's GUI. So let's start with a link training. As you remember, in order to do any measurements, the DOT has to be put into the loopback active master state. That means this device in a test will regenerate all bits received by the receiver. So let's do a link start first. As you can see on the left side, I have set up the data rate for PCI Gen 4, and if I press link start, you can see that device will go immediately into loopback active master mode. So we are now at PCI Gen 4 loopback active master mode, and actually for the given setup back to back, so direct connection between the pulse pattern generator and the error detector means that the state machine will be very simple. Nevertheless, we can have a look at it. And as you can see, we went through very few steps only from the initial state to the loopback active master state. No preset negotiations happen, but still the data rate negotiation happens. So at a certain point, we went from 2.5 gigabit, meaning PCI Express Gen 1, into 16 gigabit, meaning PCI Gen 4. So let's close this window. And once I have the DOT put successfully into the loopback active master mode, I can start the BER measurement. So that would be the receiver link equalization test if we would do a compliance test. And let's just start it. So to keep things a bit short, I have set the gating time to 5 seconds. So after 5 seconds, I get a pass result because I didn't receive any error. Now I want you to show a very neat feature called matrix scan. What does it do? Imagine that your DOT successfully went into loopback mode, but whatever preset you are trying, the bird is showing errors or even is losing sync, like this. Let's check the BR measurements here. See, there's significant numbers of errors. Just on a note, in order to stress our error detector, I had to add some significant amount of jitter. So let's close this window. Let's check matrix scan then. So let's start it. Okay, matrix scan is checking the BER depending on FIR filter coefficients or cursors, defining signal predistortions like pre-shoot and pre-emphasis. The 11 presets defined for PCI Express Generation 4 are a subset of possible cursor combinations. By scanning cursor settings with higher granularity, it is likely to find sweet spots for the DOT receiver. The engineer gets valuable hints about possible changes to design or the equalizer. Let me explain the results shown in the matrix. The color code gives you a quick overview about the BER results. In our case, it ranges from green, 0 errors, to red, to sync loss. Moving right horizontally, the emphasis increasing. Moving down vertically, pre-shoot grows higher. Increasing both the emphasis and pre-shoot have negative impact on the BER, with the pre-shoot seemingly a little bit less damaging. Maybe a change of equalizer settings in the receiver would help. Another very important analysis feature is the jitter tolerance test. A similar concept to matrix scan shown before, we measure a bit error rate against two parameters, jitter frequency and jitter amplitude. Many standards define the measurement ranges like PCI Express Gen 4 in our example. This is to ensure that the DOT receiver can handle highly jittered signals and doesn't get distorted by other system components, like an example for power supplies. During the test, jitter generation sweeps through the specified amplitude ranges with a given granularity for all specified jitter frequencies as displayed in the table. Let's start the test and watch the details. The test will start with the highest frequency of 100 MHz, and you can see how the amplitudes are changed from the lower limit 0.1 UI towards the upper limit 0.2 UI. This test will take some time, so bear with me, I will come back in a second. After the measurement being completed, we conclude a pass for all jitter frequencies. Now we can also watch the results in a graph. What does it show us? The graph shows us the sinusoidal jitter amplitude versus the jitter frequency and the measured results. So we can see that we have measured the 4 frequencies from 100 megahertz down to 400 kilohertz, and we got for every of the jitter frequency we didn't get any errors. The purple line on top shows the jitter generation limits of our jitter module, and the lower line shows the lower limit and should be covered also by the mask limit. So we have a full pass on all frequencies, so which is expected because now I was using again a back-to-back connection with no major distortions expected between the pattern generator and the error detector. Finally, we can save the results in a report, either in an HTML format or a CSV, where all measurement conditions are reported, and in the end also all measurement results. This concludes my short presentation of the analyzer's capabilities of our Anritsu MP1900A bit error rate tester system.
Thank you very much for watching my video. I hope that you found it informative and useful. Please visit us at www.anritsu.com or reach out to your local Anritsu partner. Thank you and bye-bye.